Hello and welcome to this video about vector space proofs. This time we're going to prove that the span of any set of vectors is a vector space. So this is the definition of a span. It's the set of all possible linear combinations of these vectors. It doesn't matter whether this set is linearly independent or not, because a certain vector in this set could be written in multiple ways in terms of the coefficients of these vectors. And here's an example. This vector is a linear combination of these vectors and is therefore in the span of A. And this is another linear combination of these vectors and is also in the span of A. So now we'll start the proof. We'll let these two vectors be members of the span of A. We'll define these vectors to be equal to this in terms of the vectors in the set A. If there are multiple versions of these coefficients, then we'll decide on one of them and stick to them. Now we'll have to prove that the span of A satisfies all 10 vector space axioms. To prove that it's a vector space, we'll start with the first one, which says that the sum of any two vectors in the set is in the set, and y and z can stand for any two vectors in this set. We'll expand out this sum using the definitions of these vectors in terms of the vectors in the span of A. Then we'll simplify this expression so that there is only one coefficient for each of the vectors in A. And so this vector is in the span of A because it's in the form of a member of this set. Now to prove the second axiom, it says that the product of any vector in this set by a scalar is also in the set. We'll define the variable A to be in the real number system so that it can be a scalar of the span of A. It can be adapted to complex numbers too. So we'll expand this product using the definition of y in terms of the vectors in set A. We can multiply it out using the multiplication rules for vectors. And so it's in the form of a vector that can be found in the span of A, and therefore it's in this set, which proves axiom 2 to be true. Now to prove axiom 3, which says commutativity must be true for addition. This seems obvious, but still must be proven. We'll start with the left-hand side and expand it out into what it is in terms of the vectors of A. We can swap these vectors around immediately because it's in a notation for which we can do this. And we can get it back into general vector notation, which proves this axiom to be true for this set. Now to do axiom 4, which is called associativity, which means that we can swap the brackets. We need a third vector to do this proof. We'll call it W. And we'll define what W is in terms of the vectors in A. So we'll start with the left-hand side and expand it out. We can swap the brackets immediately because these vectors are in a form that we can do it for. And we can get it back into our general red vector notation so as to prove the axiom true. Now to prove axiom 5, that a 0 exists for this set. This is its definition, and it is both a left and right 0. So we'll define what the 0 vector is, and it is all of the vectors in A multiplied by 0. Then we'll show that it satisfies the definition of 0, that it's a left-hand 0 in particular. We'll expand this expression out like this. We'll gather all of the like vectors together, and so all of the zeros cancel. And we'll get the original vector y back unchanged, showing that it's a left-hand 0. And we can similarly show that it's a right-hand 0, thus completing the proof. Now to prove axiom 6, that there's a negative for each member of this set. Adding a negative to its positive gives 0. We'll define the negative to be this, and show that it's a negative for this vector. This will be enough to prove this axiom. So we'll prove that it's a left-hand negative first. We'll expand out this expression. We'll manipulate this expression. Then we'll simplify this expression again. This gives us a vector with all of its coefficients equal to 0. And this is the 0 vector, so we've proven this to be a left-hand negative. And we can similarly show it to be a right-hand negative, thus completing the proof of this axiom. Now to prove axiom 7, which is the first of the distributivity axioms. We'll start out with the left-hand side and expand it out into the vectors contained in A. We can fairly easily use distributivity on these vectors now that we know their form. And we can convert back to generalized vector notation, thus proving this axiom. Now to prove this distributivity axiom, which is very different to the last one. So we'll start by expanding out the left-hand side. And we can easily use the distributivity property with these vectors. And we can simplify this back into the original red vectors, thus completing the proof of this axiom. So now to prove this axiom, which is associativity for multiplication, we'll expand out the left-hand side. We can easily apply associativity to these vectors, and then we can simplify them again to get this equation, and so we've completed the proof. And now for the final axiom, that multiplying a vector by 1 leaves the vector unchanged. We'll just expand the left-hand side. Multiplying by 1 does nothing to this vector, and so we get the vector back unchanged, which proves the final axiom. So now we've proven all 10 axioms, so we've proven that the span of A is a vector space. Now we'll attempt to prove these theorems that we've proven before to be true for the span of A. We'll start with this theorem that multiplying any vector by 0 gives us the 0 vector. So we'll expand the left-hand side, which gives us this vector, which is the definition of the 0 vector. So now we've proven this theorem. Now to prove this theorem, we'll expand out the left-hand side, which will give us this vector, which gives us the negative of the vector that we multiplied by -1, which proves this theorem for this vector space. So I hope that you've found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to share this video. Please leave any helpful thoughts in the comments if you have any, and thanks a lot for watching.